All right, so now we're going to move on to the use of counting techniques in probability. And in this lecture, we're going to restrict our attention to the study of uniform sample spaces. So, okay, what is a uniform sample space? So don't forget that a uniform sample space is one in which each outcome in the sample space, all right, so I'll just go ahead and write that in the sample space. Let's write here, space is equally likely. All right. So, for example, our coin flip was the uniform sample space because heads and tails was our sample space, and each event was equally likely. Right? It's just as likely to get heads as it is tails. All right. So, if we have a uniform sample space, then we can calculate the probability of an event E by just looking at the number of elements in that event and dividing it by the number of elements in the sample space. Okay? So that's all there is to it. They're all equally likely, so we just count the number of elements and take the ratio of the number of elements in the samples, number of elements in the event over the number of elements in the sample space. Okay, so let's take a look at an example. All right, so now it's a coin tossing problem, but now we're going to toss it 6 times. All right, so not just once, so it's a little more complicated. So whenever we calculate any probability involving an event, we're going to divide it. No matter what that event is, we're going to divide by the number of elements in the sample space. So before we start, let's start by calculating the number of events that would be in the sample space. Now we don't want to write all these out, every possible outcome. So, but all I care about is the number of them. So think about, we toss the first coin. How many possible outcomes are there for the first toss? There's 2. It's either going to be heads or tails. Okay, and for the second toss, we have another 2 possible outcomes, and then the third toss, and the fourth toss, and the fifth toss, and the sixth toss. All right, so there's 2 possible outcomes for each time we flip the coin. So we're just using the multiplication principle here. So we get 2 to the 6th power, and that is equal to 64 possible outcomes. All right. So, and I don't want to list all that out. You know, I'd be like, okay, one possible outcome would be heads, 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 heads. Another one would be heads, 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 tails. You know, so it would take a while to list all those out. But all we care about is the number of outcomes. All right. So now we want to calculate the probability of getting exactly 3 heads. Right? We want what's the probability that the coin will land heads exactly 3 times? All right, so we've got the denominator already. We got the number in the sample space. Now we just need the number of elements in the event, and the event we're interested in is exactly 3 heads. So, you know, this event is going to look like, now again, I'm not going to list it all out, but here's what it's going to look like. One of the outcomes is going to be heads, 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 tails, 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 right? And then it's just basically different arrangements of this same sequence of letters. So heads, heads, tails, heads, tails, tails, and so on. Again, I don't want to list it all out because that would be a pain. So what we're going to do is use our counting techniques to figure out how many elements are in that set. One way you can look at this problem is as a letter arrangement. So last week we talked about letter arrangements. So you can see we're just going to have 3 heads and 3 tails, and we just want all the arrangements of those letters. So the number of elements in E is just the same as the number of ways that we could arrange this word HHHTTT. Okay, so we have six letters. So we have 6 factorial ways of arranging the letters if they were all distinguishable, but they're not all distinguishable, so we've got to divide by 3 factorial to account for the number of ways that the H's can be arranged, and 3 factorial to account for the number of ways that the T's can be arranged. Okay, so now I want to point out too that this is exactly the same as 6 choose 3. Okay, because another way to think about this, there's only 2 ways that the coin can come up, and we want exactly 3 heads. So you could imagine, like, you know, we're gonna fill in 6 places as we toss the coin, 6 spots, and you know, we could choose, you know, 3 of those spots to be H's, and then the rest will be T's. So this the number of elements in this set is the same as 6 choose 3. Okay, and you know, and you would see that if I calculate this out, it would be 6 times 5 times 4 over 3 times 2 times 1. If I calculate this out, I get 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. I just noticed here this is supposed to be a 1. And 3 times 2 times 1. And if we cancel, 3 times 2 times 1 will cancel, right? So then it just looks exactly like 6 choose 3. And there's a reason for that, okay? So, all right, so let's just do this calculation. Okay, 3 times 2 times 1 is 6. So I cancel out the 6. And I end up with 20 ways that I can get exactly 3 heads. So the probability of this event is 20 out of 64, which is 5 over 16. Or if I want to write it as a decimal, it's 0.3125. Okay. All right, so I'm going to circle that so you see that's my answer. Okay. All right, so let's look at the next one. Now, in this one, we want at most 3 heads, right? We're looking for the probability that the coin will land heads at most 3 times. At most. Okay, so let's break that down. That's either 0 heads or 1 head or 2 heads or 3 heads. Okay, so we can have all those possible outcomes that would count as at most 3 heads. All right, no more than 3 heads. All right, so how many ways can we get 0 heads? Well, basically one way, right? That would be all tails. But we can also think about it as 6 choose 0, okay? Because we're basically choosing 0 spots to put heads and then filling everything else in with T's. Okay, I'm just going to write these as combinations at first, and then we'll calculate the combinations. Okay. The number of ways to get 1 head would be 6 choose 1, right? Pick 1 spot for the heads, fill everything else in with T's, tails. All right. The number of ways to get exactly 2 heads, 6 choose 2. Number of ways to get exactly 3 heads, that's what we just calculated up above, 6 choose 3. Okay. Now, I'm going to show you a different way to calculate these combinations. So you remember Pascal's triangle. I'm just going to recreate it here, off to the side. So all I'm doing is I'm just adding the 2 numbers above to get the next row. 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1. Okay, so I've got what I need, and I can just read now the combinations right off of Pascal's triangle. So that's a really nice quick way of finding a combination. So I know now that 6 choose 0 is 1. 6 choose 1 is 6. 6 choose 2 is 15. And 6 choose 3 is what we got before, which is 20. Okay. All right. So that's a total of 42 ways. 42 ways. And so that is the number of elements in the event I'm interested in. So the probability of the event is just 42, equals 42 out of 64, which reduces to 21 out of 32. And if I write that as a decimal, I get 0.6563. All right, I'm going to circle that one. That's my exact answer. All right, let's keep going. What is the probability of getting heads on the first and last toss? All right. Well, okay, so the number of elements in the event. Now this one is probably easiest to just use the multiplication principle. Okay, so if you think about, okay, we want heads on the first toss. Okay, there's only one way to do that. Okay, for the second toss, we don't really care, so there's 2 options for the second, 2 options for the third, 2 options for the fourth, 2 options for the fifth, and then the last toss, we want that to be a head. So there's one way to do that. Okay, so that's probably the easiest way to do that. That is 2 to the 4th, which is equal to 16. Okay, so I just used the multiplication principle. So the probability of my event is just going to be 16 out of 64, which is 1/4. And that's 0.25 as a decimal, of course. Let's circle that one. All right, one more in this problem set. All right, this is one I've indicated that you try it. So if you'd like to pause the video and give this a try, and then come back and I'll show you how I got the answer. All right, so this one, we're looking for the event where we get exactly 4 heads. Exactly 4 heads. Now we've already calculated exactly 0 heads, exactly 1 head, 2 heads, 3 heads, so we're just going to do this the same way. We're looking for the probability of exactly 4 heads. So the number of ways to get 4 heads is going to be 6 choose 4. Okay? And because of the symmetry, now I could actually just read that right off. 6 choose 4. This is 0, 1, 2, 3, and 4. So 6 choose 4 is just 15. I can just use my Pascal's triangle for that. So that's what I'll do, since I've got that right there. So the probability of getting exactly 4 heads is just 15 out of 64. And I can't reduce that. That's my answer. As a decimal, I get 0.2344. All right. So the trickiest thing here is just to remember your counting techniques. And counting techniques take a bit of practice to get good at. Okay, so now let's look at another example. In this example, we've got a big bin of DVDs, 100 DVDs, and for some reason 10 are known to be defective. So if a customer selects 6 DVDs at random, what's the probability that 2 of them are defective? All right, so we're looking for the case where exactly 2 of the 6 DVDs that we choose are defective. All right, so first of all, every time we calculate probability, we need the number in the sample space. So how many ways are there to select 6 DVDs 6 DVDs from 100? Well, that's just going to be 100, choose 6. I could calculate that out, but I'm not going to do that right now. I'm just going to leave it in that form. Now, if we are interested in 2 of them being defective, what that means is that when we select these DVDs, we want to choose 2 defective DVDs. All right, and we want 4 non-defective. All right, DVDs. All right. So let's think about it in that terms. We're going to deliberately choose 2 defective DVDs and 4 non-defective DVDs. All right, so the probability of this event happening is just going to be, all right, we're going to choose 2 defective DVDs, and there are 10 of them. We're going to choose 2 of them. So there are 10 choose 2 ways to choose the defective DVDs, but then we also have to choose the non-defective ones. So we're going to use the multiplication principle with these 2 combinations. The number of ways to choose 4 non-defective DVDs from 90, right? So there's 90 non-defective DVDs, and we're going to choose 4 of them. So we're just going to calculate 90 choose 4. And if we multiply those 2 together, then we've got our task complete, right? We've selected 2 defective and 4 non-defective. All right, and then we want to divide that by 100, choose 6. All right. So now I could write all of that out, as far as what I would calculate. I use my calculator on this one. And so I didn't write it, well, I did write it all out, but I ended up using my calculator. Because you get, this 100 choose 6 is 100 times 99 times 98 times 97 times 96 times 95, and then you divide that by 6 factorial. So it's a big number. So long story short, here's the answer. 0.09646. Okay? So about a 9% chance of choosing 2 defective DVDs. All right. What is the probability of choosing at least 1 defective DVD? Okay. Well, so at least 1, if we're choosing 6, right? So at least 1 would be 1 or 2 or 3 or 4 or 5 or 6 defective DVDs. So that's a lot of casework. The easiest way, whenever you see at least 1, think about complementary counting. So what's the complement of at least 1? The complement of at least 1 is none. So what I'm going to do is I'm going to count the complement. And the complement is no defective DVDs. All right? So if we're going to choose no defective DVDs, there's 90 non-defective DVDs, and we're going to choose 6 of them. And there are 100 choose 6 ways, total ways of choosing the DVDs, so the probability is 0.5223. Okay, that's the opposite of what we want. We actually want the probability that we have at least one defective DVD. Okay, so the probability of at least 1 is the opposite of what we just calculated. All right, so we're just going to take 1 minus 0.5223, and we get 0.4777. Okay, so that's our final answer, is about 47.8% chance that we're going to choose at least 1 defective DVD. All right, so here's another one that says you try it. So go ahead and pause the video and give it a try. Okay, so we want the probability of the event where we get 3 defective. Okay, so 3 of them are defective. Okay, so it's a lot like this part A. Here we wanted 2 defective, now we want 3 defective. So we want to choose 3 defective and we want to choose 3 non-defective because we're choosing a total of 6 DVDs. So we've got 10 defective DVDs. We want to choose 3 of them. And we've got 90 non-defective, and we want to choose 3 of those. All right. And then we're going to divide by the total number of ways. 100, choose 6. All right. And when you calculate that out, you get 0.1183. Alrighty. So you got to get good at these combinations. Alright, so let's try example 3. So it looks like I've labeled it as a you try it problem. So go ahead and pause the video. Take a look at this. It's very similar, but go ahead and try it. Alright, so we have a bunch of light bulbs. We have a lot of 24 light bulbs, and we're going to choose 2 of them. Now, out of that 24, we know that 4 are defective. So this is really a lot like the DVD problem. Okay. Now, the number in the sample space that we're going to use as a denominator in all of our probabilities is just going to be 24, choose 2. Yeah, 2. Because we're choosing 2 light bulbs. Okay, so there are 24 choose 2 ways of selecting 2 light bulbs from a lot of 24. All right, so the first question asks us to look at the probability that we have 2 defective light bulbs. Okay, and we're only choosing 2, so what's the probability that both of them are defective? All right, well, okay, so we've got 4 defective light bulbs. We're going to choose 2 of them. And that's it. We don't want any non-defective ones. All right, we're going to divide that by the number in the sample space, which is 24, choose 2. Okay, so when you do that calculation, I got 0.02174. All right, second part of this question asks, what's the probability of getting at least 1 defective bulb? So at least 1 is defective, so 1 or 2. Now we already calculated 2, so we could just calculate 1 and add them together because those are mutually exclusive events. You're either going to get 1 or exactly 1, or you're going to get exactly 2. Okay. So, or we could use complementary counting, which, yeah, let's just go ahead and do that. Since it says at least 1, it's just begging to be counted as a complement. So the complement of at least 1 is no defective. No defective bulbs. All right, so no defective. So we have 20 bulbs that are not defective. We want to choose 2 of them. And the total number of ways to choose the light bulbs is 24, choose 2. So we end up with 95 out of 138. Okay. I just did that by writing it all out and canceling factors. So I didn't actually calculate what that is as a decimal, but so what I'm going to do is I don't need the number of ways to choose no defective light bulbs. I actually want the event that we have at least 1 defective. Okay, so that is just going to be 1 minus the probability we got above, 95 out of 138, which is 43 out of 138. Okay, and as a decimal, I got 0.3116. Okay, that's the final answer. All right. Now, we get to move on to the birthday problem. And the birthday problem is a famous problem. Because there's an unexpected result in certain cases. Now, I'm just going to look at the basic concept behind the birthday problem first. All right, so we're dealing here with a low number of people. A group of 5 people selected at random. Okay, the question is, what is the probability that at least two of them, let me underline that, at least 2 of them share a birthday. Okay, we're going to assume that none of the 5 people was born on a leap year, or at least February 29th of a leap year, and we're going to assume that each person is equally likely to have any of the 365 days in a year as his or her birthday. Okay. Now, this says at least 2. Now, that's not quite at least 1, which was the keywords that I told you to look for complementary counting. But if you think about it, at least 2 people sharing a birthday is 1 pair of people sharing a birthday. So this, another way to say this is that, what's the probability that at least 1 pair of people share a birthday? So, all right, well, okay, so let's try doing the complement. So what is the complement of at least 2 people sharing a birthday? So the complement of that is none share a birthday. And that's a lot easier to calculate than to try to calculate the probability of at least 2, because we could have 2 sharing a birthday, or 3 people, or 4 people, or 5 people, or yeah. So I guess we could only go up to 4 if we only have 5 people, right? So it's only, yeah. So anyway, okay. So let's all right. None share a birthday. That's our complement. Birthday. Okay. So let's calculate the number of ways. What's the probability that no 2 people share a birthday? So that means 5 different birthdays. Okay, so 5 different birthdays. All right, so how many choices do we have for the first person's birthday? The first person's birthday could be any one of 365 days in the year. Now the second person, we can't pick somebody who has the same birthday. So that person only has 364 possible birthdays in order to satisfy our criteria. And then the next person can't have the same birthday as the previous 2, so they could have any one of 363 possible birthdays. The fourth person, 362, and the fifth person, 361. Okay, just because we're going to eliminate any people who have the same birthday as any of the previous people. All right, so we're just using the multiplication principle. And how many possible, in total, how many possible ways, how many possible birthdays could we have? Well, essentially we have 365 possible days and 5 people, so it would be 365 times 365 times 365 times 365 times 365, so 365 to the 5th power. And if you put that into your calculator, you get 0.9729. All right. Now, that's the opposite of what we want. We're interested in the event that at least 2 share a birthday. Okay, so that's the complement. let's count. So we're going to take 1 minus the complement, the probability of what we don't want, and I get 0.0271. Okay, so that's not so remarkable. That's not likely at all, which is what we would expect, right? I mean, you kind of expect that it's unlikely that, you know, that in this small group that you're going to have 2 people with the same birthday. Okay, so that's kind of what you would expect. So why is this such a famous problem? Because this does not seem particularly remarkable, this particular result. But let's take a look at what happens. I'm going to scroll down here. Okay, so I'm just going to scroll down here a little bit. Oops, went too far. Okay, so let me see here. Let me scroll down just a little bit. Okay, so now what if we look at 30 people? So this is a little bit more interesting if we look at 30 people. So what's the probability of, let's look at the complement just like we did above. What's the probability of 30 people all having different birthdays? Probability of 30 different birthdays. Okay. Well, so that's just going to be, now what we had above was a permutation, right? It was 365 times 364 times 363 and so on. So that's just the permutation. And in this case, it's going to be permutation of 365 taken 30 at a time. Okay, because we got 30 people, and we want them all to have different birthdays. Out of 365 to the 5th power total ways of having birthdays. Okay, so if we calculate that out, you get 0.2937. Okay, so the probability of at least 2 share a birthday. Okay, so at least 2 share a birthday is just going to be 1 minus 0.2937. And for that, we get 0.7063. Okay, now that's very likely, right? That's more than a 50% chance. If you just have 30 people, there's a 70% chance that 2 of them will have the same birthday. So that's pretty likely, that's the part that's unexpected. You wouldn't expect it to be that high. You know, it seems like, you know, and I think the way people think about it is they think about it from their perspective. What's the probability of somebody having my same birthday? Now that is low, okay. But the thing here is that we're looking for any 2 people to share a birthday. So if you think about how I would ask that, like, you've got 30 people in the room, and I ask, does anybody have, do any 2 of you have the same birthday? You know, no, you're not going to know until you like ask everybody else in the room if they have your same birthday, right? And you think about all those different pairs of people that, you know, would have to ask each other their birthday to even find whether anybody has a shared birthday. That's a lot of different pairs, 30 different people taken 2 at a time. So what is that? 30 times 20. That's a lot of pairs, 700 and something pairs of people would have to ask each other a question. Is your birthday whatever? Okay. So that's why this is an interesting problem. And I think it became famous back in the 70s because Johnny Carson, now I don't know how many of you know Johnny Carson, he was the host of The Tonight Show before Jimmy Fallon, before Jay Leno, back in the 70s, okay? And back in the 70s, you know, most people only had 3 channels. and you had ABC, NBC, and CBS. And so if you watched late night TV, you watched Johnny Carson. You watched The Tonight Show with Johnny Carson. So a lot of people saw that so on his show, he tried to test this hypothesis. And there's a video, if you, I'll probably post it on Canvas, where, you can see he's asking, he brings up this birthday paradox, and then he proceeds to ask somebody in the first row what their birthday is, and then he asks the whole rest of the room, does anybody share that birthday? And no. Because the probability for that one particular person is very low. Okay, the only way you can figure out if any two people share a birthday is to like have everybody ask everybody else. So he asked the wrong question, so it was a total failure, and so I think that's why it became a famous problem. But if you look at this, it only takes, okay, this is just a table of, okay, so here's the number of people. This is what we calculated first. We calculated this 5. There was only like a 2% chance that if you have 5 people, that any two share a birthday. So as the number of people increase, here's what happens to the probabilities, right? The probability increase. The more people you have, the more likely it is that 2 people will share a birthday. But it increases a lot quicker than you would expect. And it only takes 23 people for there to be a 50-50 chance of 2 people sharing a birthday, which is really interesting. And if you have only 50 people, you have a 97% chance that 2 people will share a birthday. So that's really interesting. So that's it. That's all I have for this lecture. All right. See you later.